Thank you everyone for your interest in this presentation. I'm Sijia Geng, a postdoc from Laboratory for Information and Decision Systems at MIT. This talk presents our current work on optimal co-planning of distributed energy resources for battery and hydrogen electric bus fleets. The transportation sector has been reported to account for around 15% of global carbon emissions. In the developed regions, such as the United States and European Union, this number is even higher to the level of around 30% of total emissions. Therefore, decarbonizing transportation plays a crucial role in achieving the target of zero carbon emission by mid-century. Recently, the European Union has approved to end the sale of combustion engine vehicle by 2035. It is urgent to shift to clean energy technology, and the key direction for achieving this is through transportation electrification. Promising pathways to electrify transportation include shifting to battery electric vehicles that draw electricity from the grid or local renewable generations, and fuel cell electric vehicles that utilize zero or low carbon fuels such as hydrogen. Battery EVs has already gained momentum in recent years. The left figure shows the increasing battery EV sales in Europe. The top right figure shows the potential of hydrogen-based economy in the future. Based on this source, hydrogen is predicted to play an important role in transportive applications such as heavy-duty vehicles. Moreover, hydrogen refueling would take much less time compared to EV fast charging. Zooming into the local area, MBTA, the local transportation authority in Boston area, has set a plan to convert the entire bus fleet to zero-emission technology and invest on associated facilities to reduce carbon emission. In this work, we will utilize realistic data from MBTA to analyze the potential and impacts of using electric bus fleets to cover transportation demand. Both battery electric and hydrogen fuel cell electric vehicles will have large impacts on local energy distribution systems. Our goal is to investigate the impacts of fast charging stations and hydrogen refueling stations on local electricity distribution systems. We aim to fill in the gap in analyzing the impacts of renewables and on-site local hydrogen production on optimal system design and operation. The novelty of our work is that we designed an optimization tool for co-planning the infrastructure at the depot and the electric vehicle fleet. The optimization tool is able to handle large-scale realistic transportation systems. The left figure gives an illustration of the overall composition of infrastructures at the depot. The upper part represents the electrical system of the depot. It is composed of various distributed energy resources, including wind turbines, solar panels, and battery storage. A connection to the grid is also included as a backup option when the local renewable generation is insufficient. The lower part shows various hydrogen delivery, production, and refueling components, which are modeled to represent the infrastructure supporting hydrogen fuel cell EVs. Hydrogen can be generated through electrolyzing water, which is an entirely carbon-free method. Otherwise, hydrogen can be generated through a reforming process, which uses natural gas as the feedstock. Hydrogen delivery via truck is also an option. The produced or delivered hydrogen is then stored in a hydrogen tank, which will then be compressed to a high-pressure storage buffer before being dispensed to the vehicle. The electricity usage from these various hydrogen processing devices interconnects the electrical system with the hydrogen system at the depot. The red figure shows a satellite image of the Boston Cable Bus Depot. The total roof area will enforce certain limit on solar panel installation capacity. The key challenge of our planning problem is that realistic transportation system has complex and large-scale trip schedules. Conventional formulation tracks the charging and operation for each vehicles and chargers. This is intractable to scale up for the full number of trip schedules and considering multiple vehicle and charger types. In this work, we propose an integer clustering formulation. We group vehicles and chargers by type and manage charging and energy at the group level. This figure illustrates the idea. We consider 3 vehicle types, and each of which have multiple buses. We track the total energy stored in all vehicles at the depot that are of the same type. When a vehicle leaves the depot to start a trip, sufficient energy needs to be carried in that specific vehicle. Similarly, we only manage the chargers at the group level instead of managing the individual charging. Through manipulating constraints on the energy carried in the bus on trip, the integer clustering formulation can give rise of both an upper bound and a lower bound on the true solution for the individualized formulation. We work with real fleet demand data from MBTA transit schedule. The schedules are complex and represent timescale information that should be included in our investment planning problem. We select 8 representative days to capture the 8 season and day types, differentiating the weekdays from the weekend. The route distance are calculated from shapefiles, and we refer to a block as the collection of individual trips that start and end at the depot. In the planning problem, every block needs to be covered by 1 vehicle. Decisions will then be made about how many vehicles and chargers and associated infrastructure need to be built. We adopt a time of use electricity tariff based on the new ISO New England wholesale market price signal. Furthermore, a monthly demand charge structure is enforced to penalize the peak demand charge, and a higher price is set for summer months. For hydrogen delivery via truck, a fuel cost of $10 per kilogram is assumed to reflect the status quo. In the case study, we investigate 3 types of battery EVs from the Proterra DX5 product line, and 1 type of hydrogen fuel cell EVs from the New Flyer Celsius. 3 DC fast chargers with different charging levels are considered in the study. Note that level 4 DC fast charger is very cheap compared to level 5 and only slightly more expensive than level 3. Hydrogen refueling nozzle is also much cheaper than DC fast chargers, but introduce much higher power rating. Based on the optimization results, to support the given transportation demands, we need to invest on 3 types of battery EVs of various quantities and 9 level 4 DC fast chargers. Currently, the high cost of hydrogen delivery and on-site production prevent the hydrogen fuel cell bus from being deployed. However, among the various choices of distributed energy resources, solar photovoltaic is chosen to be built up to the capacity of the site. Recall that our integer clustering formulation gives rise of both an upper bound and a lower bound. In this example, there's indeed a gap between the 2, suggesting an approximation error to the individualized formulation. The energy stored in each vehicle type, each consisting of multiple buses, are shown in this figure. The drop of the curve indicates a vehicle leaving the depot to start a trip, and the increase of the curve mainly suggests charging at the depot. We can see that the energy level at the end of the day returns to its starting value to maintain a continuous operation. The charging power from the grid is shown in the left top figure. We can clearly see that due to the higher peak demand charge in the summer months, the peak demand in summer is lower than the other seasons. Also, with each representative day, typically the time of use is higher towards 7 p.m. when people return to home and start to use appliance. We can see that the system avoids drawing electricity from the grid around that hours, but will charge later in the day to restore the energy level in the vehicle fleet. The red figure shows how much of the total fleet demand is met by solar panel. We can see that this charging power follows well from the power generation from solar photovoltaics. These two figures show the number of vehicles at the depot versus those are actively being charged. We can see that at most of the time, only a small portion of the vehicles are being charged, which explains the relatively small number of chargers being built. This reflects the fact that we are charging the vehicle smartly by optimally switching charging between vehicles. In summary, this talk makes a novel attempt to represent the complex dynamics between energy system and vehicle demands in future transportation systems. We provide realistic insights into the evolution of future interconnected electricity, hydrogen, and transportation systems. For future work, we plan to look into the effects of different electricity and hydrogen pricing structure on the planning results. From the analytic perspective, we will analyze the accuracy of the integer clustering formulation. The planning results will be disaggregated to give the individualized vehicle operation dispatch. And this concludes my talk. Thank you.